right, so this is section 3.2, part 2. We're going to talk about differentiability, what that means. So here's the definition. Given x aught is an element in the domain of f. So a function f is differentiable at x aught if the derivative at that point exists. Meaning a function f is differentiable at that point if f prime at x equals the limit as h approaches 0 of f at x plus h minus f of x over h exists. Okay, so basically if you have a slope of that function, then it exists. Okay, so this is a two-sided limit. One way to interpret this is that the slope of the secant line from left and the slope of the secant line from the right both have to exist and be the same value. If they don't, then the function is not differentiable at that point. So number 2, the function at x is differentiable on an open interval ab if f is differentiable at every number in the interval. Okay, so here's how a function can fail to be differentiable. If we look at the first one, if we have a corner, you guys see this weirdness right here? It fails to exist because of this area right here. If you have discontinuity, then the limit from the left is not the same as the limit from the right. Okay? And also, if we have something funky where it changes like that, this is the slope at that point. That is a vertical line, like x equals something, right? And that's a problem because if you remember, if x equals a number, the slope is undefined. Okay, because it is a vertical line. Okay, so these are a couple ways that a function can fail to be differentiable. Okay? So if we look at example 3, given y equals f of x, where is f of x discontinuous? And where is f non-differentiable and why? So let's look for discontinuity. Discontinuity means where we have jumps or something doesn't exist, right? So here's a point because I have a hole there. So we can write down x equals 1. That's one place where it is doesn't work. So f equals -1. Also, where x equals 1 is a problem child too because it doesn't exist at that point, right? So it's discontinuous at where x equals 1. So now where is it non-differentiable? So once again, we're looking for corners. We're looking for, discontinuity or someplace it would make a vertical tangent line, okay? So if I look at this, I see a corner right away, which is right here. Where does that happen? Where x equals -2. That's a corner. Okay. I also got a problem where x equals 1. And the reason why is it's discontinuity. Okay. And then we also have an issue where we have a corner here. So that's a problem child. So x equals 2 is a corner as well. And finally, at this point right here, my tangent line is now vertical. So when x equals 3, we got a vertical tangent line. Okay. So there's a theorem. It says if f is differentiable at a, then f is continuous at a. Differentiability yields continuity. Continuity at a does not imply differentiability, though. So you can't go the other way around. Just because it's continuous does not mean it's differentiable. Okay? But if it's differentiable, it does mean it's continuous. Okay. Now, example 4, which you guys have a larger copy that'll be easier to see, it says match the graph with each of the function with a graph of its derivative. Okay, so here's how I do it. What I would do is draw in lines, around this function, and these lines are tangent to the function. So if I look at the first line that I draw, I see that it's positive. And then this is 0, and then it becomes negative, right? So when you have a positive, that means it's above the x-axis. Whoops. How did I skip back there? And then it gets to 0, and then it goes below the x-axis. Okay, so let's see what matches up with that. I need something that's above the x-axis, then when x is 0, it's 0, and then it goes below the x-axis. So if I look here at 4, I can see that it's positive until we get to 0, it hits 0, and then it gets negative, right? So it's below the x-axis. So once again, on the left of 0, it's above the x-axis, then it becomes 0, and then after 0, it is below the x-axis. So 4 is the solution for the first one. Let's check out the second one. Okay, so if I put tangent lines in here, it looks like that. So the slope is positive, 0, negative, 0, and then positive again. So we're looking for something that's above the x-axis, 0, and then it hits 0, right? So it hits the x-axis. Then it gets below the x-axis, comes back up, hits 0, and then is above the x-axis. So let's look for anything that hits the x-axis more than once. So if I look at this, I'm looking for something that does that. And if I look at number 1, that kind of does that, right? Because it hits the x-axis twice. And it's above the x-axis, just like we said, hits 0. And then it's below the x-axis, hits 0. And then it's above the x-axis again. So I think I is our one that we want. So let's look at C. So what the heck is the tangent line? The tangent line is the line itself, right? So the tangent line is constant. It doesn't change. It doesn't change from positive to negative slope, right? So I'm looking for a constant line, and if I look through my choices, I can see that I is the solution to that because it's constant. Let's look at D. Okay. So once again, it's constant, and we're looking at this, and we have a negative slope, right? And then it zeroes out, and then we have a positive slope, right? So I want a constant line that's below the x-axis, and then at 0, I need a constant line above the x-axis, okay? And also, we see we have a what? That's a corner. Hopefully you said that. So we know that it's non-differentiable at that point. So there's going to be a break in the graph. So let's see if we have any breaks in the graphs. If I look at it, I see I have 6 and 7 that does that. But the only one that fits the bill, because we have constant slope here and here, is going to be 7, which is VII. Okay? So do you see how it broke? Because remember, it's non-differential at a corner. Let's look at E. So the slope on E is positive, and then we have another corner again, so we know there's going to be a break, and then we have negative slope, right? So I need something that's above the x-axis, breaks, and then below the x-axis. So I look at that, 6 fits the bill because it's positive above the x-axis, breaks, and then negative below the x-axis, okay? All right, so let's look at F. So what's the tangent line? It's flat or 0, and then it's positive. So I'm looking for something that's flat for a while or close to 0, and then it shoots off and becomes above the x-axis. And if I look at that, the answer is going to be 3, because look at this. It's constant, and then it becomes above the x-axis. And let's look at G. So G, if I put in those tangent lines, I have this, which is positive slope. And then it kind of flattens out, still positive, but it gets less positive, if you will, right? So I'm looking for something that's above the x-axis, and by process elimination, we have 5 left. But if you look, all of this is above the x-axis, and it kind of flattens out. So the answer to this is going to be 5. So once again, when you do these, when you match them up, your best bet is to kind of make lines and see if your slope is positive, 0, negative. If you have a corner, we know it breaks. And remember, if it's positive slope, it means that your graph is above the x-axis. If it's a negative slope, then it means it's below the x-axis. So I hope that helps you. So I'm going to do another video for the last page of our notes. So you're going to have another part. So go ahead and watch the next one.